So we talked about pH. I'm not sure what day number that was. We talked about titrations earlier, and we talked about pH earlier. But what we're going to be after here is being able to get a skill in order that will allow us to predict the pH at the equivalence point. So in other words, a lot of these processes, chemical processes, you know, making wine or diesel fuel or drugs or whatever, titrations are really powerful. What we've used them for up to this point was to determine the amount of something. It could be a poison. It could be whatever and compound. You want to figure out the amount of that. You want to figure out its concentration. Titrations are great for that. But titrations can also be used to figure out what the pH is going to be at the end of this reaction. So, and you want the reaction to completely end. You don't want to add any extra stuff because then you're wasting money, whether it's the wine process or the pharmaceutical industry or the biodiesel fuel. At the end of a reaction, when all those reactants are gone, you want to know what the pH is because that's important. I mean, acidic properties, basic properties, that really affects your system. So it's really useful to know what the pH is. So that's our big goal. And we're going to divvy this up into two parts because it's kind of a lengthy calculation, lengthy prediction. Okay? So first we're just going to figure out today how to set up this calculation, how to set up the prediction. And then part two will actually get the final answer. At the equivalence point, the pH will be. Okay? So let's go ahead and get started. We'll do a little review first. I changed this morning from what's in your notes, but it's pretty much the same thing. We're going to try to predict the pH at the equivalence point. Let's do a little review first. This is a picture of a titration setup. And let's say it's a titration of a weak acid with a strong base. So which solution goes where, Andromeda? Right? Here's my weak acid and strong base, either over here or in the picture. What goes where? If I'm titrating a weak acid with a strong base, where does the weak acid solution go? Where does the strong base solution go? Because the English, I think, is confusing from right off the get-go.
I think doesn't the base go in
The base? Yeah, what is this guy called? The burette, exactly. So there's where my base will go, my strong base. Because when you're titrating something with, right, that's the strong base. So my weak acid will go down here. Exactly. Okay. So at some point during this titration, Enrique, so that means we're, like Andromeda said, our burette, and there's our little valve, right? So we'll open and close it, right? We'll keep adding that strong base. But at some point, we're adding that strong base so that the moles of the strong base added exactly equals the moles of the weak acid. So stop adding strong base. Because, Connor, what? Because the blank point is reached. Yeah, you'd think equal points would be a great word for it, but that's not the jargon they used. The E, here it is, the equivalence point. Technically, you're supposed to say the end point, but if you pick the right indicator, yeah, because you have to put some indicator in there, right? Otherwise, you don't know when to stop. So we'll put some solution in here that'll change color, but because the equivalence point is reached. And the equivalence point is the end point if you pick the right indicator, so we won't worry about that. We'll just call it equivalence point. So what we're going to try to do is predict the composition at the equivalence point of an acid-base titration. In other words, just how much of it do we generate? What's the concentration of it? Okay. Now let's do this one step at a time here. We've got a table. Alyssa, give me a name of a weak acid from that table. I don't know if you can read your table, but sulfurous acid. There it is. She picked the bottom guy, H2SO3. Sulfurous. Okay. Give me a name of a strong base, Cameron. Any strong base. I'll give you a hint. Something hydroxide. And you've got 1, 2, 3 shots at this. Something hydroxide. He could name sodium hydroxide, potassium hydroxide. They're all right down there in alkaline earths. Or lithium hydroxide. You never hear that one though, right? We're always using sodium hydroxide. So let's just pick that one because that's so common, right? Okay. There's also calcium, strontium, barium hydroxide, but I don't hardly ever see those either. Okay. Mia, assume your chosen weak acid, that sulfurous acid, is titrated with our base. So as the titration progresses, a conjugate blank is being produced. Right? Because this H2SO3 is being titrated with the NaOH. And we're just trying to put names for this stuff. The H2SO3 is supposed to be a weak acid. H2SO3 is the, what word did we call this? Anybody help her? The blank acid. It's what form? It's the conjugate acid form, right? And then it has a conjugate base form. Now, Alyssa picked an ugly one because it has 2 hydrogens on there, right? Oh, it says monoprotic, doesn't it? She can't pick sulfurous acid. Because there's 2 hydrogens. Back to the drawing board, Alyssa. Pick one that only has 1 hydrogen on it. What did you say? Nitrous acid? Is there such a thing? Oh yeah, there is. HNO2. Gosh, that doesn't even sound common, does it? Nitrous. HNO2. All right. So, see, it only has 1 hydrogen. That's what monoprotic is. So Mia, we're back to you. So we're titrating NaOH with HNO2. As the titration progresses, a conjugate blank is being produced. What's the jargon? Are we producing a conjugate base, a conjugate acid, or neither one? We're producing a conjugate base. Does everybody agree? Because the NaOH is reacting with that HNO2, which is a conjugate acid, so it's going to form a conjugate base. Everybody agree? Kenneth, you agree? Okay. When the equivalence point is reached, only this conjugate will be formed, and it will be, what is it? Steph, what is it? What is this conjugate base going to be? NO2 minus. Perfect. Right. It's almost like a population game. You've got so much HNO2 and so much NO2 minus, but you're starting out with HNO2 because that's what's in the bottle, right? So it's a weak acid, so it's pretty much all HNO2. And then you add NaOH, all that HNO2 gets eaten up because it's an acid, NaOH is a base. You produce the conjugate base NO2 minus. And you better quit because Enrique said stop adding NaOH, right? So it's only NO2 minus at the equivalence point. Since only this conjugate is present at the equivalence point, that solution is going to be what, Audrey? Acidic, basic, neutral, not enough info. All you have is NO2 minus. It's going to be basic because NO2 minus is everybody, it's a base. It's not very strong, it's a weak base, but it's a base, so it's got to be basic. What is the chemical equilibrium? I already picked on Andrea. Jose, what is the chemical equilibrium that controls the pH of this solution at the equivalence point? Now remember, all you have is NO2 minus. You have to write a K, here's a hint, you have to write a K what reaction? Did you hear? KB. You have no choice because all you have is NO2 minus. The only reaction you can write is KB because all you have is NO2 minus. So you write a KB reaction. So Megan, what KB reaction are you going to write? What goes to what? Well, reactant. NO2 minus How do you write a KB reaction?
Oh, okay.
How do you write a KB reaction? Plus H2O. Now you're on track again. Plus H2O goes to OH negative, HNO2. That is the equilibrium that controls the pH. Okay. Predict the equivalence point. If 55 mils of 0.15 molar solution of the acid is titrated with 0.21 molar NaOH. When they say predict the equivalence point, what are the units of your answer? Connor, what are the units of your answer when they say predict the equivalence point? Milliliters. Because it's a fancy word of saying how much of that darn NaOH do you add, and you better stop after you add that volume, right? So he's right, milliliters of the NaOH. He kind of got you started, Kenneth. How are you going to figure this out? We want to know so many mils of NaOH, and that's going to be our answer. How are you going to figure this out? Anyone got a hint? Anyone got an idea? Andrea, what are you going to do? It's a leap. It's a big leap here.
Where do you start from the 21 molar, 0.21 molar
You could. Okay, now we have two options. We can head out where Megan's heading out. I'm not sure which one you're going to be more comfortable with. We can start out with the 0.21 molar NaOH and work backwards and try to get milliliters of NaOH out of it. It's going to be kind of complicated because you can't even really start with 0.21 molar NaOH. You have to start with it flipped, right? Because molar is what over what? Moles over liters. We want our answer to be in liters, so we better start with liters over moles. You have to start with that flip, so it's kind of complicated. What I suggest starting with is the logic. The logic dictates that at the equivalence point, the moles of this acid is exactly equal to the moles of what? NaOH. So really what we're going to do is we're going to set up that big M equation. That 0.21, right, is going to be moles over liters, right? We just need to find out what this is. Find it, and then we'll solve for the liters. Right? Remember doing this game? So we'll find the moles, divide by liters. You know what the moles are. Because at the equivalence point, the moles of the acid is equal to the moles of the NaOH. And I think one thing you just got to get used to is when they give you a volume and a concentration, you know moles. You know moles. You know grams. When they give you a volume and a concentration, you know moles. Right? You just set up the big M equation and you'll have it. So do this first. Find the moles of that acid. And whatever you get for the moles of that acid, you put it in over here, solve for liters, convert it to mils, and you got it. Try it. See if you can get it. See if you can figure out what the equivalence point is. And that number is going to go right there. Because they're the same. Do you see now why we had to get on Alyssa's case for not picking a monoprotic acid? Because if it wasn't monoprotic, this isn't going to work. We're going to have it's not one-to-one. Okay? So it'll be more complicated. So we're only going to mess with monoprotic acids. So did you get 8.25 times 10 to the negative 3 for the moles? Right? Now solve for liters. That's going to go to the top. This goes to the bottom. So 8.25 times 10 to the negative 3 divided by 0.21. Okay, and that's the answer in liters. So I got 0.039 liters, which equals how many milliliters? 39. Yeah, just move the decimal place over 3 times. Okay. Cameron, did I lose you? Where did I lose you? Right. You're after the equivalence point, so that means you're after, I think it starts with what Connor said. You got to know what you're after. You're after the moles of the NaOH. You're after the moles of the titrant. You're after the moles of what's in the burette. So this is the moles that you better add, then you stop. And you stop because at that point, the moles of what's in the beaker and the moles of what's in the burette are exactly the same. That's why you stop. And we know the moles of what's in the beaker because they told us the volume and the concentration. Okay. Okay. One last step. I added this. You don't have this in your handout. You might as well just finish it. Now, predict the concentration of the conjugate formed at the equivalence point. So we are calculating the concentration of what? What do I put in the brackets? What are we looking for? What conjugate are we trying to find? What's formed at the equivalence point? The base, which is NO2 with a negative. So this is what we're trying to find. Okay. So you have the concentration of anything. That's what over what? Moles over liters. And I'm going to write the word total volume because we're adding this NaOH the whole time. Because you can't say the volume is 55 mils, right? Because you have the weak acid in here, right? The strong base is in there, and you kept adding it until, dang, right, you hit exactly 39, then you stopped. So the volume down here is no longer 55. It's what? How do you get that total volume? 55 plus 39 milliliters. And it has to be in liters, though. Right? So this total volume, that'll be 55 mils plus 39 mils. Okay? But it has to be in liters. How about the moles of NO2 minus? What would that be? Yes, it's this one. They're all the same because you started with all moles of the acid. You have so many moles of it. It all got converted to the moles of the conjugate base. It's got to be the same number. And it was converted by adding that same number of moles of the strong base. That's how it got converted in the first place. So all those moles are the same. The moles of the strong base you added, the moles of the weak acid you started out with, the moles of the conjugate base you end up with. They're all the same. Because it's that titration. It's the equivalence point. So you already got that number, 8.25 times 10 to the negative 3. So it looked like an ugly question, but really I don't think it was. The final answer, I got about 7.76 or so times 10 to the negative 4. Did you get that? No? What'd you get? So 8.25 times 10 negative 3 divided by 0.055 plus 0.039. Really? I probably screwed up. 8.25 times 10 to the 3 negative. Yeah, it has to be in liters. Oh, and I got 0.08.
The milliliters have to be in liters.
Has to be in liters, yeah. So now I got 0.088 or so.
You convert them there or afterwards?
You got to convert them first. So this should be, we should change it right here. 0.055 plus 0.039. Okay? Good deal? All right. Here's the whole ball game here. We're going to, we have 100 mils of 0.38 molar hydrogen cyanide. And it's titrated with 0.5 molar NaOH. So again, a weak acid titrated with a strong base. What conjugate acid or base is formed at the equivalence point, and what is its concentration at the equivalence point? So just what we did. So you need to figure out, identify what the conjugate's going to be, and then determine its concentration. Right? So want to do this together, or you want to work on it? Together? All right. Well, no problem, because Enrique is going to tell us what to do. Enrique, what's the conjugate that we're going to form? Yeah, what will the chemical formula be? It's going to be a base. You're right. It's going to get a conjugate base. Because we're starting with what weak acid? HCN. It's going to be CN negative. Our answer is CN negative. All right. Okay. And what we can do, I think you should do something like this. Let logic help you out, because you're going to look at this and say, well, where do you start? Where do you start? Well, what is its concentration? I would write down what concentration is. Moles. And then if you remember that this is a titration, instead of just writing like moles over liters, right? If you put more description in there, that really helps. You could put moles of cyanide all over liters total or something, because you know that you're adding stuff. So you can't just divide it by the 100 mils. You got to also add the what point? Equivalence point. So you got to add that total liters. You have a good chunk of it. It's going to be 0.1 liters plus, you got to figure it out. The equivalence point. So Alyssa, I see two things to figure out here. I see one, we got to figure out the top, the moles of cyanide, and then we got to figure out the bottom part, the equivalence point. Which one do you want to work on? The bottom one? Okay, how are you going to do it? Where are you going to start?
So you have to take the 0.5
Take the what? I think it'd be easier to start up here, because this one's a multi-step. This one is one step. Do you see how the top is easier? The top just has to be what? Andrea, what does the top part have to be? Yeah, she's setting up the big M equation, or she actually has done this so much. Did you hear what she said? She said it's 0.38 times 0.1. Exactly. Whenever you know concentration, it's big M times liters, and you always get moles, because the liters cancels. So she's done this enough, she knows. She knows, hey, I can just take these two right here, And I'll know the moles of HCN. I'll know the moles of conjugate acid. But then I also know the moles of conjugate base. I also know the moles of the NaOH that I've added. I know them all. I know all three. They all got to be the same. So she's exactly right. This is going to be 0.1 liters times 0.38 moles per liter. Or you can set up the big M equation if you want. Same thing. Top part's done. And the top part really helps you figure out the bottom part. So see if you can figure out the equivalence point and get a final answer for this. All right. Hopefully you set the big M equation or just figure it out using units. Yep. Okay, then that's the added volume, because before we just had 100 mils, but now you actually have 100 mils plus this volume, because this stuff is diluted.
So then add it on the bottom.
Yep. So your total make that your total volume. You get about 0.076 for the volume of the NaOH. So if they ask for the equivalence point, your answer is 0.076 liters or 76 milliliters. Either one would work if they asked for the equivalence point. But they didn't. They just want to know the final answer. So I got about 0.216 as the final answer. Okay. Connor, you got that? All right. Then the last part, they wanted you to write the chemical equilibrium occurring at the equivalence point that controls the pH. So Mia, what reaction would you write? What chemical reaction controls the pH? All right. What conjugate is present at the equivalence point? What's the acid or base that's present? It's Cn minus, right? Because all that, there's no NaOH, it's all reacted. There's no HCN, that's all gone. All that's there is Cn minus. So that means you have to write a Kb reaction. Cn minus plus water, HCN plus hydroxide. I don't know if you noticed, but it's always going to be this way. If you're titrating with a base, you always get a base at the equivalence point. If you have a base, you have to write a Kb reaction. So whenever you titrate with a base, you're going to have to write a Kb reaction, so you end up with a base. Titrate with a base, you get a base. And one other thing I want to leave you with before we go on to the next question is all that we're going to do for part 2 is take this number right here and do the ice table. And then we'll calculate pH. Do what we did before. That's how we're going to get the pH at the equivalence point. We're just doing all the hard work today. I think the next part's going to be a lot easier because we're doing all the hard work, getting the initial concentration of the conjugate base that's present at the equivalence point. Okay. Find the Ka or the Kb. How do we do that? Kendall. That equilibrium demands a Ka or a Kb. Which one are we trying to find? Trying to find a Kb. All right. Now, sometimes there's tables. We could get lucky stuff because there's some weak bases that have a table and they have the Kb listed. Is Cn minus going to be one of those? No, it's not. Don't waste your time looking in the table of Kb's for Cn minus because it has a minus sign on it. It's not neutral. It's a conjugate. So you have to look up the what and calculate it. Look up the acid, the Ka, and calculate it. Because you remember Kw was Ka times Kb. So Kb is going to be Kw over Ka. 1 times 10 to the negative 14 all over HCN. See how good my eyes are here. I can hardly read this stuff. Here's HCN. I think it says 4.9 times 10 to the negative. Is it 10? 4.9 times 10 to the negative 10. Thanks. So 1 times 10 to the negative 14 divided by 4.9 times 10 to the 10 negative, and you get about 2 times 10 to the negative 5. So at the equivalence point, the pH is going to be anybody? Basic, exactly, because it's a conjugate base. So when we go and calculate our answers, we better get a number bigger than 7 for pH. Okay, just see if you can get part A done, and then we can call it a day. Now notice here, you're not titrating with a base, you're titrating with a acid. So you're going to get a acid. That's the big hint. Okay. How do you write the conjugate acid of ammonia? NH4 plus. Good deal. It's a conjugate acid. You need to find its concentration. Figure out the moles of it. That's the easy part. And then figure out the total volume. Divide the two, and you'll have its concentration. Did you add the 2 to get this one? You did, right?
Yeah.
Yeah, okay.
Okay, but this has some K since we've gotten acid already.
Yeah, so what you have to do is, you can't find a table that has the Ka for NH4 plus in it.
Go for the NH4.
You have to go for the NH3 and find its Kb, and then calculate Ka.
NH3 plus H2O.
No, this is NH4 plus. And you have to write a Ka reaction. Right? So hopefully you're getting this. And don't get stuck in a rut. If you know this, you titrated with an acid, so you're going to get an acid, so you have to calculate a K. You have to write a Ka reaction down here, because you have an acid. And that's always the conjugate acid goes to H plus and the conjugate base. So you need to calculate a Ka. And there's no table of Ka for it, so you probably have to use ammonia's Kb and calculate a Ka. Did anybody get a final answer for what's the concentration of ammonium? Did anyone get a number? 0.11? 0.113? Good deal. So come by if you have some questions.